Hello YouTube. This is the final session of the low level design series. So basically I started off with low level design, and the idea was I'm going to take up a question every single day and I'm going to try to solve that question and record my progress. Why I did this is because initially I didn't have a very high level of confidence in low level design. So I think on the first day what we had done is we had come up with a framework on how to answer these questions, and then applied that framework to create a game of blackjack. Day two was when we did our library management system. We created a library management system. Day three, we ended up doing Stack Overflow, where users could post questions, write comments, rate questions and answers. And day 4 was LRU cache, least recently used cache. Day 5 was yesterday, which was a coffee vending machine. This was a pretty interesting problem. And what I do is I just go online and I try to find a good low level design question and I implement it, right? So low level design problems. Yeah, so from this repository I end up taking any one of the questions and I end up doing it. So today's day 6, and I think today is going to be the last, at least for now. So these 5 sessions of low level design I've done on consecutive days. So for the past 5 days I've been doing this, and today is the 6th day. I feel going through this exercise has given me some really decent level of confidence in low level design, and at this point I think after today's session I'm going to take a step back and kind of reevaluate where I should put in effort, because I feel like initially it was justified that I'm putting in effort to gain confidence in low level design, but now since I have that confidence I feel there's better use of my time. So I think today we're going to do one question, but after that we're going to take a break from this and see if there's something else we should be putting efforts into. Maybe later I'll come back to this series when I feel I need to practice, but for now this is probably the last video. So let's find a problem for today. So this is the group of questions that we have. Let's kind of find some sort of what is a music streaming service? The music streaming service. Let's look at this. It seems a little interesting. So you can browse for songs, albums and artists. Users should be able to create and manage playlists. Should support user authentication and authorization. Users should be able to play, seek within songs. The system should recommend songs. How are you gonna stream songs in a low level design thing? Maybe this is a little too big for the scope I'm going for. Let's look at something else. Social networking, Stack Overflow, task management, tic-tac-toe, traffic signal. So one second, what all have we done till now? We have done one game, which is a blackjack game. We have done coffee vending machine. We have done so coffee vending machine was more about inventory management. Blackjack was basically a game. Library management system was sort of multiple users borrowing resources, I guess. LRU cache was more around data structures and algorithms and time complexity, and Stack Overflow is where users can ask questions and do that sort of thing. What else can we do? We can do a movie ticket booking system. We can do so the music. Although this seems interesting, the music streaming service, I don't know how are we gonna play songs. I mean, will we have to keep a list of songs in a folder and then get a library to play those songs? But I feel like that's too much for the scope of one interview, so I don't think any interviewer would expect you to do that. Maybe it's just it just prints out okay playing song and it prints out the seconds, but it kind of defeats the whole purpose of the music streaming service. What else is there? We have an online auction system. Auction listings. It's a multiple user system basically. We have a food delivery service. Elevator system. This seems interesting. Elevator system should consist of multiple elevators serving multiple floors. Each elevator should have a capacity limit and should not exceed it. You should be able to request an elevator from any floor and select a destination floor. Elevator system should efficiently handle user requests and optimize the movement of elevators to minimize wasting time. That is very interesting. I feel that kind of gives us, that's an interesting problem statement, right? Because depending on how many elevators are there, depending on whether the elevator is for an office building or a residential complex, it could be a sort of different kind of algorithm for each. System should prioritize requests based on the direction of travel and proximity to the elevator to the requested floor. Elevators should be able to handle multiple requests concurrently, process them in an optimal order. Yeah, let's do this. Yeah, this seems pretty interesting. I'm gonna pick up the requirements from here and create a new folder called elevator question.txt. So I think the first thing in our requirements, the first thing in the framework that we developed was closing the scope. So just as an overview, the framework that we had developed in the first video of this series, the one in which we created a blackjack game, is as a first step what we do is we try to understand the problem, and as a second step we close the scope of what we are trying to do in this particular session, and the scope includes both functional as well as non-functional requirements. Post that, we start to think about what kind of classes and entities are there going to be, what kind of variables are there going to be in every class, how these classes are going to interact with each other, and what would be the behaviors of each class. And once we've kind of hashed that out, and there's like basically zero ambiguity in what is to be implemented, at that point we start our implementation and just do it based on what we had discussed or what we had decided. So we're gonna do the same thing over here. We are gonna note down requirements. This is basically the scope of what we are trying to do. So we have an elevator system, should consist of multiple elevators, so we need multiple elevators are needed, right? Each elevator should have a capacity limit and should not exceed it. Is it fair to say that each elevator has the same capacity limit, or it has a different capacity limit? Let's keep it as the same. Each elevator has the same capacity limit. I think it's the same makes sense because in a real setting, if you think about elevators, if you go into a building, irrespective of which building it is, most of the time the elevators will have a similar capacity, unless there's a distinction between service elevators and normal elevators. There is usually the same capacity limit. Okay, so elevators should have a capacity. Users should be able to request an elevator from any floor and select a destination. Okay, users can request elevator from any floor and go to any destination. I think one interesting thing over here is, since users are sort of requesting the elevator and going from one floor to the other, we don't really need to capture user information over here. Like the user names and are really not relevant. Who called the elevator is not relevant to our elevator system, which is kind of different from like a library management system we did a couple of days back, because there we kind of needed to store the fact that this particular person has borrowed a book. Okay, so the elevator system should efficiently handle user requests and optimize the movement of elevators to minimize waiting time. Okay, so we need to optimize for minimization of waiting time. Awesome. And then the system should prioritize requests based on the direction of travel and the proximity of the elevator to the requested floor. I mean, to be fair, the factors based on which we are prioritizing the request should be the factors which come up which minimize waiting time, right? They should not be telling us to use these factors. If we can come up with or find some other factor which is more pivotal in minimizing waiting time, then we should probably optimize for that, right? Why should we prioritize for the direction of travel and proximity to the elevators to the requested floor, right? It's a little confusing, because the problem is it says that we should prioritize requests based on the direction of travel, which kind of makes sense, I guess, but it should also do it based on the proximity of the elevators to the requested floor, which kind of means that if we are pressing an elevator on 3 and if there are like a couple of elevators close to 3, it's basically saying it shouldn't go in the opposite direction unless there's no requests pending, and it should kind of, the elevator closest should go there. Okay, I think I got what it's saying. So if there are two lifts and one lift is both the lifts are going down, one is on the 4th floor, one is on the 5th floor, and you request a lift to go down on the 3rd floor, the lift on the 4th floor should actually stop instead of the 5th one. This makes sense because we are optimizing for minimization of waiting time over here. The other thing is that requests should be based on direction of travel. This is interesting, right? Because this is different from minimization of waiting time. Imagine if both the lifts are kind of going up, right? They're going to the 9th floor and you're requesting on the 5th floor to go down, right? Now that also sort of prioritizes waiting time, because waiting time can be considered in a couple of ways. It's either waiting for the lift, like if we define waiting time as the time the user is waiting for the lift, that's one definition. The other definition would be the total amount of time the user took from the time they requested a lift to the point where they reached their destination. And if we use that as a metric, then I think we can, if a lift is going up and we request it to go down, the lift should not stop and pick you up on its way up, right? Only when it's going down should it pick you up. So, okay, we can do that. Elevator should be able to handle multiple requests concurrently, process them in any order. Not in any order, process them in an optimal order. Okay, system should ensure thread safety and prevent race conditions. As with previous questions, the thread safety and prevent race conditions is just using a lock. We're not going to do that, to be honest. It's the same code, it's just that you add a lock implementation to it, and wherever in your code you're entering a critical section, which is usually when you modify some sort of a data, you kind of wrap it inside a lock. Like you have to acquire a lock before accessing the critical section. So I think that's about it. Let's talk about classes. So that's why we're not really too concerned about the system should ensure thread safety part of it for now, at least. Let's look at classes. Okay, so we need a, so what, one second, what do we need, what are we doing? We need a elevator management system, probably, right? So we need some sort of a class which can have, which kind of understands where each elevator is at currently, I guess. right? Do we need an elevator class? Elevator class. And what kind of information would the elevator even store? This is interesting. Actually, let's go through the user journey, and I think that will be a bit more clear what classes we would like to use, because currently it kind of feels a little vague as to what we want to do. So the user comes and requests a lift on a particular floor, right? So when we talk about the request which comes in, at this point we don't know where the user wants to go, I guess, right? At that point, do we already know where the user wants to go? No, right? The user will enter the lift and then kind of decide. So the request would basically have a direction and it would have some floor value, right? That's all the request object initially would have. And once the lift actually, so this information should be enough to tell our elevator management system whether the lift should stop over there or not. And once the lift stops over there, we have basically another kind of request in a way, right? Which has, so we can do an open request over here, and we can do actually let's call it source requests and destination request, right? Because destination request would now have a floor, which is the destination floor, and there will probably be no direction on it. So once the user is inside the lift, based on the source request, the lift opened up, the user went inside it, and a certain destination request was taken from the user, which has just a floor, right? And this is not a list. I'm just using any brackets to show that what all things are going to be there in it. So user comes, puts in a source request. Those source requests are sort of managed by the elevator management system in a way that it informs the lifts where to stop. And once the lift does stop, we need to take in another user input, which would be the destination request, right? And okay, so once we take the destination request, the elevator management system would again it would instruct the lifts on where to go as a destination, and the lift would go and go. And in the source request, once the lift stops here, we'll update that we're increasing the capacity, like some of the capacity of the lift has been filled. So based on the capacity of the lifts and the direction of the lifts, the source request would get basically serviced. But from a user's perspective, I think these two are the only requests. When we talk about an elevator instance, an elevator could have so when I talk about classes, we have a elevator management system. Do we want to keep like a request management system as well, or we can just keep that within the elevator management system? The source request, like it will come in to the elevator management system. Probably let's keep it as 1 for now. And we have elevator. The variables the elevator would have is current capacity, right? Current capacity as in how many users are currently in the lift in this particular elevator. It would have the current flow. Do we need to actually do we want to store which floor this elevator is on within the elevator class itself? Oh, how is this gonna work? Management system would, so this guy would have multiple elevators, right? The elevator management system has essentially has a list of elevators, and whenever a request so each elevator would have probably a current state, right? the current state represents so the current state would be represented by a tuple which, by two variables essentially: the direction the elevator is kind of going in and the current floor of the elevator, right? These two things would kind of define the current state the elevator is in. It has a direction and it has a current floor, right? And the elevator management system basically has a list of elevators, and each elevator has a current capacity, current state, direction, and a current floor. Okay, and now when we talk about the behaviors, we'll have a source request, right, which takes in a direction and a floor, and we're gonna keep it static. Elevator management system, when we're initializing it, it would also have the total number of floors, right, and it would have the number of elevators. I think the number of elevators is in this list itself, and we have a total maybe total floors, right, max floors or something like that. And then we have a a source request, which can happen. We have a destination request which can come up, which just has a floor. We also kind of need to have instructions for the elevators, right? Like, what should the elevator do now? And that can keep changing. Like, for example, for a certain elevator, we said that, okay, if a user got in on floor 0 and said, I want to go to floor 7, we gave the elevator an instruction to go to floor 7. But when, suppose, a new source request comes in at floor 5, saying that I also want to go to maybe floor 6 or something like that, the elevator should ideally stop at floor 5, right? So the instructions given to the elevator gets okay. So I think one thing we need to keep in mind is that the instructions given to an elevator changes, or rather needs to be reconsidered every time a new request comes in, right? Every single time a new request comes in, we need to kind of understand and reevaluate basically the next instruction that we are giving our elevator. For example, if the user comes in with a source request at 5 at the direction of up, we are going to give some sort of a instruction to our elevator that you need to stop at this floor. And then basically a destination request will come in, and based on that destination request and the older destination requests which the elevator was already servicing, it would decide what to do next. So we do need to store this somehow, right? So the elevator needs to have a set of instructions, I guess. And the set of instructions, maybe we can keep a queue for each elevator, right? And that queue could have okay, so maybe like an instruction queue, which is basically a list, right? List of, let's say, instructions, and we're going to define what an instruction is, right? Maybe we can keep an enum of instruction. That enum can probably have what to do next, right? And an elevator can just go to a basically not an enum, but maybe just another class called instruction. And instructions are in the format of floor number, right? That's pretty much it, right? That you go to this floor would be effectively an instruction. So the current capacity, current state, which has the direction, and maybe we can take current direction separately. Do we want to keep the current floor? Yeah, we kind of need to understand. Yeah, I think current state was fine. We have the direction and the current floor. I think for better readability, we should probably have a current direction, two separate variables, one for current direction and one for current floor, because we would need quick access to these, right? So the current direction may be some sort of a boolean or maybe an enum, and current floor is an integer which is probably less than the total flows. Okay, so based on a source request, we check the elevators to see which elevator is basically closer, and we also check whether that elevator can service the current request. And suppose for example if both the elevators are going up, or suppose we have one elevator which is going up and there's a request to go down at 3, at that point the elevator, either it's possible that the elevator is has full capacity, in which no elevator is actually available, so that instruction comes into play only when there is capacity in the elevator. Like once the current capacity is maxed out, basically the elevator can't take any more instructions, I guess, right? It has to service the instructions already. Yeah, so basically I think one caveat here is that when the capacity is full, stop taking instructions, right? We can't take any more instructions if we are at full capacity, because how is anyone else going to come into the elevators? Only when someone leaves the elevator, like some of the instruction queue gets serviced, is when we even have a capacity to take any requests, right? So suppose we can take a request, right? Suppose the lift is going up right now, it's at 4, and someone at 5 is like the lift is going up to 10, and someone at 5 wants to go down, and they put in a request that okay, I want to go down. We kind of have to put it in the instruction queue somehow, that so there are two scenarios here, right? If the user wanted to go up, then it has to be prepended to the instruction queue, is the first thing to be done, because now there is capacity and we can pick that person up while going up. Otherwise, if it's not in the same direction, then it kind of goes to the end of the queue, right? So we need to check two conditions. So we need to check conditions: is the floor on the way, and is capacity available? Now capacity available will already be checked, but is floor on the way, plus is it the same direction, right? So if it is on the way and is in the same direction, then basically prepend the instruction, else postpend it, right? And it the direction we can take from current direction and the current floor we have, so we can kind of make out whether it's kind of going up or going down, and we can check whether we want to prepend the instruction or not. And okay, there's basically a time tick, right? So we will just has something called a time tick, which would effectively simulate the lift's next state, right? So the time tick would basically keep simulating where the elevator is going. So there has to be function here, print state function, which is going to print the current direction and the current flow and the current capacity. What else can an elevator do? I think that's it, right? We keep an instruction queue. Let's kind of do a run through it. whiteboard. Let's open a, yeah, so what we were thinking about is that we're going to keep a queue of instructions, right? And suppose we have a lift which has a capacity of 5 people, and maybe there are 2 people in the lift. We have 5 floors, and the lift is going up from 0 to 5th floor, right? So at this point in the instructions, what does the instruction look like? It just has a floor number, right? Wait, does the instruction only have a floor number? Yeah, right. So initially we knew that the direction of the lift is going up. At that point we had put 5 in the queue, and we know that the direction is up at this point, right? Suppose we encountered 2 requests, right? One request we encountered at 3 and one request we encountered at 4, right? And at 3 it was saying that, and the lift at this point was at level 1, right? And at level 3 it was saying that I also want to go up, so the direction is the same, the capacity is available, there's like 1 person waiting over here, and the lift it's on the way, it hasn't crossed 3 yet. So we I guess add to the queue, and we say that okay, you kind of need to stop at 3 now. And at 4 we get a request, but we see that the direction is completely different, so we add 4 here, which makes sense. It'll go to 3, it'll go to 5, it'll go to 4, right? At this point it makes sense. Now suppose it reaches 5, at which point once it's reached, the next one is 4. So we know that, you know, the direction changed because the next destination is below. And at that point, so this would have gone and the direction would be down, and it would be going to 4. At that point, if a request comes in, suppose this was 6 and request came in at 5, yeah, it would have just come at 5. Yeah, I think that works. I think that works. So I think we can start coding this out. Let's see how it goes. Hello. Okay, so we have our classes, right? So let's say we have, you know, instruction is just a floor number, so I think we're good on that. We have a class called elevator. Let's define the what do you call the constructor for this, right? And it would have, what all did we want to keep in the elevator class? Current capacity, current direction, current floor, and instruction queue, right? Okay, so we need the current capacity, current floor, max capacity. I think we'll just add it. Current capacity, direction, floor, current capacity, floor, direction, current direction, and an instruction queue, which we'll just initialize. So we have self dot current capacity, which is equal to probably 0. Self dot, actually current capacity is 0, right? So we maybe just take in max capacity. Actually we don't need to take these things. Self dot current floor is just, we assume it starts from 0. I think it's a fair thing to assume. And then current direction also we can assume, right? So it doesn't really take much. And the max capacity we can in fact hard code. Do we actually want each lift to have a different capacity? I think we can just hard code it for now. So let's keep it as 5 people, right? And the current direction, we probably need to define what a direction is. Let's look up real quick how to do in enum. Yeah, I think in yesterday's question I had used an enum. So the direction, I think we'll just keep it as an enum. So let's say this is direction and up and down. If you're wondering why, this doubt was in my mind earlier when I had started coding about 5 years ago. Actually, much more than that, right? Yeah, started coding about maybe 5, 6, 7, 8 years ago, 8, 9 years ago. That why are we using enum? I thought it was, why, like if they're just two variables, why can't we just use some variable and just call it 0 and 1, like an integer object, and just say 0 and 1 instead of creating an enum of up and down. And now it makes sense to me, because when you define an integer takes up some amount of space. It could be a 32-bit integer or 64-bit integer, and it would end up taking 64 bits of space. But when you talk about an enum, since I've only defined two values in an enum, this is actually only going to take 2 bits of space, right? So memory wise it's efficient, and also it kind of makes the code more maintainable, because we cannot have any other value except for up and down here. But if we end up using an integer with 0 and 1, if someone adds a 2 somewhere by mistake, we don't have a check against that. So yeah, that's why enums are keep getting used. Anyways, so we have an elevator class, we have the current capacity, current floor, the current direction. Let's just pick up a direction dot up, right? And that's pretty much it. So actually that's not it, right? We need a instruction queue as well. Awesome. Self dot instruction queue, which is equal to an empty list at this point. And let's give it a couple of behaviors, maybe an add instruction function, right? Takes in a floor. So at this point our elevator management system is going to poll the elevators. It's going to read the current capacity, the floor, the direction, and it's going to come up with an instruction to give to a certain elevator, and it's going to call the add instruction method of that elevator to give it the instruction, right? So and the instruction is of type just floor, so which is of type int. So suddenly we have, and at this point we just need to append. Actually there are two operations, right? There's a append instruction, like in which you prepend and append, right? Add so we need actually two functions here, prepend instruction, and we would need append instruction, right? But this isn't that readable, to be honest. Let's do add instruction to end. Or maybe just keep it as add instruction, and we'll add a parameter here which represents to end, add to end, and this is a boolean, right? Now based on whether this add to end is true or false, we can decide whether to prepend or append, right? So if add to end is true, we need to add to the end of the queue, right? And how do we add to the end of the queue? How is the queue even working, right? We have a queue, and we are basically, one way is we remove stuff from the beginning of the queue and add stuff to the end. The other way is we add stuff to the end and remove stuff from the beginning of the queue. We can go with either approach, to be honest. And there is an else, by the way. So add to end, let's keep it simple. We say that we are going to add to the end and take it out from the beginning. So when we say add to end, we're just adding to the end of the queue, which is the end of the list. So we do self dot instruction queue dot append and the floor, right? That's it. And if add to end is false, it means we have to add to the beginning of the queue, right? So effectively we need to actually shift all the elements to the end, right? So okay, so we're gonna do an append operation, but we also kind of need to shift that to the beginning. So how do we shift that? So we have yeah, for I in range, the length of the self dot instruction queue. This is not add instruction, it has to be instruction queue over here, right? So you know, we loop through the queue. Suppose there are 4 elements in the queue, the I will go from 0 1 to 3, and what we want to do effectively is let's see, Python, sorry, Gemini, and loop from the end of the queue. Oh, it's just reversed, right? And I want to then add element to beginning. Oh, okay, so Python has a method for that. Interesting. That's a pretty bad example because you know which one is Python list insert method. So can I look it up? So the first one is the, one second, what just happened? Yeah, orange got put on index 1. Yeah, so it's just insert, right? Yeah, we don't need to do anything. Instead of append, we just use insert. We say 0 comma floor. That's it, right? So if it's add to end, we just append to the end. If it's from the beginning, we insert it over here and execute instruction, I guess. Execute instruction. Okay, so what does executing an instruction mean? It means taking the next instruction and updating the state, right? Taking the state, I guess that's what it means. So we take the next instruction, right, and that would be self dot instruction queue dot pop, and we take the first one, right? So we got the instruction which is basically a floor, and then we say self dot current floor is equal to this. The instruction, you know, it won't have just a floor, right? We also kind of need to know how many people are there, I guess. So it won't be just a floor, it'll actually be floor plus you know, people, capacity, yeah, load or something like that. Yeah, so we also need to know the load. So floor and load, right? It'll be a tuple effectively. And you know, when we pop this out, we have next instruction, which means we have the floor value as the the first element in the tuple, and the load value as the second element in the tuple. And then we have self.current floor is equal to this, right? So we reached this floor, and oh man, 1 second. So there's more to this, right? When we reach current floor, it's yeah, that it's probably two kinds of request as well. Oh man, this is, I think I underestimated this. 1 second, we need an instruction class as well then, because this instruction is getting a little bit complicated. So we will keep an instruction class, and we'll define a constructor in it, and we'll add everything over here, right? An instruction can be, so instruction, what all can it have? It can have a type, right? And we'll define a instruction type, let's say, right? And this is also probably an enum, right? And this would have a request, or there were two things, source and destination, right? Source and destination. Right? I guess there is one condition over here as well. Like, suppose the lift is on 2 and it's going up, and you're pressing the lift button at 3 and you want to go up. The lift is already going up, but the lift can only take one more person. So the capacity isn't full. The lift can take one more person, but there are 3 people outside who are in the same group. Should the lift stop or should the lift not stop is the question. Yeah, because I'm trying to think of, should source also include a parameter for how many people are there. One way to simplify this is that we can just say that every single request and basically every single request will be of one person. So when we have a request, it's for one person, and when we have, I think every single request we can keep it as one person, right? So we have a floor, so we don't need to keep load effectively. I think that makes sense. For this question, we're gonna just say that every single request is for one person. So we have a floor and an instruction type. Instruction type we still need, right? Is it a source instruction or is it a destination? So instruction class, I think we can avoid, but we don't need, because the load will always be one person, right? And like, for example, if 3 people want to get in at 3 and want to get out at 5, we'll have 3 requests representing that. And when we reach 5, all 3 of those requests will basically just get executed. So I think it's fine. So, but we do need an instruction type though, because over here when we execute an instruction, we pop the next instruction. We don't have a load, but we have a type, right? So we got a load and a type. Now it kind of depends. So if the instruction is being executed, that means that it can be accommodated, I guess, because now if if it was add capacity and you get a instruction type as source, the lift stops, opens up, and no one can get in. So I guess the elevator management system would never actually commission that request in the first place. So I think since we are executing an instruction which was given to the lift, it can be executed. I think that's a fair assumption. If type is equal to instruction type that's source, right? So basically this means someone is getting into the lift, right? and you know, we got the floor, so we can definitely update self dot current floor to floor, I guess, because we know we're at that floor. And if it's a source request, it might change the direction as well, right? And the other one is if it's a destination request. So let's kind of think about this, right? If it's a source request, that means that someone is getting on, so we can say that self dot capacity plus equal to 1, right? Yeah, and we can just be assured that it hasn't breached max capacity, because you know, this condition is checked while giving it an instruction. So I think this is but what if it gets breached in between? What happens then? We kind of have to, don't we have to keep in account how many people we are planning to pick up? Like for example, if a capacity has if a lift has a capacity of 3, it starts from 0 and you get 5 requests coming in to go to 10 at each at different floors. So 2, 3, 4, 5, 6. But the capacity is 3, but at the time of the request, we did not have that capacity, right? So ideally, we should not be taking the other instructions, or maybe we should take them, but we cannot accommodate them over there. So we, oh man, we keep them afterwards when at a point where the capacity is not present. Huh. So what do we do over here? We have a floor, we have instruction type source, we have current capacity. So when we are executing the instruction, do we want the current capacity to be modified at that point, or when we are taking in the request, do we want to keep that, right? So when we do an add instruction, maybe at this point we should do it, right? Right, depending on what kind of instruction it is, we should be updating the capacities so that we know, like for example, if there's a lift which already has 3 requests to pick up 3 people, it has a capacity of 3, we know that this lift probably doesn't have any more capacity at this moment. We should just wait, right? Yeah, I think it makes sense to update it over here. So if floor and what is this instruction type? Oh, this has to be passed, right? Yeah. Let's say type of instruction type. Right, and we say that this has type, and we say if type dot if type is equal to instruction type dot destination, then you do self dot current capacity is minus equal to 1, right? Else this could cause more issues, right? I think one problem over here, there's another problem over here. If the lift like if the lift is going up and we know it's at full capacity, but we get an instruction to go down, should we count that in the capacity? Because it's possible that people can get off the lift in the same time. Like for example, I mean, that running sum should be effectively 0, right? Or the max capacity. The running sum of the instructions should be preserved in a way, I guess. Like if I think about the okay, so we had a, I don't know, we had a floor and a type, right? So we had a type which is instruction type. So we had a, suppose 2, here a source as 2, and then we have a 3 source and 4 source, right? So we picked up people over here. When we encountered 2, we got a destination as something like maybe 10. So we picked up 3 people. We know at 10 we're going to deposit 1, and at 3 we also got a 10D, and at 4 we also got a 10D. And we know we basically are picking up 3 people, and those 3 people are going to get off at the 10th floor. But at this point, if we get 5 source, right, in the opposite direction, so this is probably up and we get down, according to us we should actually add 5s over here, right? But the problem is that when you consider this will be +1 +1 +1 -1 -1 -1. Oh, it'll already add -1, right? So the current capacity would take that into account, I guess. So the current capacity is effectively the running sum of the capacity. So it works when we have to add it to the here, but what if we want to add it here, right? If suppose at at maybe, let's assume at 2.5, at maybe we won't be able to add it, right? Because the capacity at that point will be 3 only after it reaches 10, because if the capacity is full it won't service any requests. So only at this point, when the capacity goes down, will this get serviced. Yeah, I think it works. I think it's fine. Anyways, yeah, so when the type is equal to the destination, we remove 1. If the type is equal to the source, we probably just add 1, right? And this is does this updating this, does it depend on what are we doing it in the end or the beginning? I don't think it does. So we just we can add it independently over here, I guess. So irrespective of which one this executes, this update step happens everywhere, right? Update the capacity. And now in execute instruction, we've already sort of accounted for the capacity once it was in the queue. Like for example, if it was a destination, we've accounted for the fact that one person is getting out, because we also had added source, right? So we are accounting for both of them. So I think in execute instruction we actually don't want to do anything. We just have to pop the last instruction. That's pretty much it, right? We pop the last instruction and we maybe just print it out. That's pretty much it. We probably update current floor. I think that makes sense. Maybe current direction we can update. Let's first print out the current state, right? The current state would have floors, would have type, right? And the current floor has been updated. How do we figure out which direction to do, right? So we need to see if there is a change in direction or not. I guess we need to kind of make out whether there's a change in direction or not. So how can we make that out? We see which floor we are on, and we see the current direction, and we see the next, right? So we see the, so we know the floor we are on. The current direction we also kind of know, which is self dot current direction. So we need to at least peek at the next request, right? Next request, which would be the self dot instruction queue at 0, and we just want to see, we're just interested in the floor, right? Next request floor, right? And now we have to check, right, if the self dot current direction is equal to direction dot, so if it's going up, and right, if the lift is going up and the next requested floor is strictly greater than or equal to, I guess, the current direction is up, but the next floor is smaller than the current floor. I think this should be enough to change the direction, right? And we also kind of need to change the direction in the other way as well. That if this was down, and the next request floor was greater than the current floor, the self dot direction would also update to probably up, right? So, and then we just print out the current direction. Floor type direction. So okay, we got it. Okay, we got the execute instruction, we got the add instruction. Hopefully they're both fine. We'll probably try it out with one lift first. I feel like this is really complicated model to keep in my head. We'll have to test it out. Anyways, so let's kind of go to our elevator management system, right? Because our elevator class seems to be complete. Class elevator management system. Quick time check. It is about 1 hour. Okay, def init. Let's start off with our constructor of the elevator management system. It will keep a list of elevators. Elevator for now, maybe single elevator would do, but whatever. It will take total floors, max floors, probably an int. Capacity we're keeping as 5. Self dot max floors equal to max floors. Self dot the elevator list is probably that's probably list, and we can create elevator objects. So basically we have 2 elevators now, right? Okay, this will work, right? We create an elevator object, it's kept in the list. Yeah, I think that's fine. So we have 2 elevator objects over here. What else? So we have a source, take source request. And it basically takes floor object, right? Maybe just we can keep a single function also and just add a type over here, which would have source or destination. Each would anyways have a single object. So if type is equal to instruction type dot destination, so someone is getting off, or maybe source. So at this point, what do we need to do, right? This is the other one. So effectively, we need to find the optimal elevator to give this instruction to. right? And we need to issue the instruction. These are the two things we need to do, I think, in both these scenarios. Maybe probably wait till we can give the instruction as well, right? Like, it's possible that it's like impossible right now to give an instruction in the first place, and if that is true, then if we're not able to give an instruction in the first place, then I guess we do this time tick or whatever. We wait. We execute instruction essentially, right? So we check. We need to check. So for each elevator in self dot elevator list, we check if elevator has capacity. If elevator dot current capacity is smaller than elevator dot there's max capacity. So here means it's possible to take a request, I guess. So there'll be some elevators which probably can't take a request, some elevators which can take a request. If there are more than one elevators which can take a request, then we need to check which one is like more optimally positioned to take that request, I guess. Okay, potential elevators, I guess. Elevator indices, right? Maybe like an empty list. At this point it's possible to take a request. We do this dot append for each elevator in elevator dot list. Maybe index for each I in range of this, right? And it's 1 second. Right, we got the elevator and then we append the index that this elevator can take a request. There is a scenario where this entire for loop sort of finishes and this basically doesn't meet, right? In which case we'll probably have to repeat this for loop. Maybe get candidate elevator lists. Let's kind of take this for loop over here instead. Right, potential elevator indices, it goes through the elevators, it checks if it's possible, and then finally it just returns the potential elevator indices, right? And over here this will be equal to self dot get candidate elevator list. It doesn't take in an argument, and this is equal to none. And while this is still equal to none, we sort of keep doing this, right? So if this is equal to none, we sort of execute this. 1 second. So we execute this once and we realize that it's none. If it is none, then we need to execute the instruction on each elevator, right? So for execute the instructions on each elevator, right? So for elevator in self dot elevator lists, v2 elevator dot execute instruction. So yeah, basically what we're trying to do is, if all the elevators are filled with capacity, we need to actually see what the next step is and execute something. So at this point, for each elevator we execute an instruction and then call get candidate elevator list again, in which case this current capacity would be updated, because I think when we execute the instructions, while adding the instructions we were updating this, right? So maybe while executing also we kind of have to do that. Yeah, I think we'll probably have to do that, right? Huh. Instruction type. So if it's a source, what did we do when it was a source? It was a source we did, so we basically take this up and we say that if it was a destination we were removing. So since so when we were adding the instruction for a destination, we were saying that people are getting off. So we had removed to account for the people who are getting off. But when we actually reach that and execute that instruction, we also remove what we had accounted for, right? So what happens if we don't update the current capacity in this? If you don't update the current capacity while adding the instruction, suppose it became filled, right? Suppose we kept getting source instructions, we got 3 source instructions, it got filled, and we got 3 destination instructions as well, and those also kind of, that freed up the capacity. Yeah, if they already freed up the capacity, we don't need to change this, right? Yeah. Yeah, sorry, where was I? Take requests, right? So we got our potential elevator indices, and no, but the problem is this, right? So here, if we are not able to service the requests, suppose we got 3 source instructions, so the capacity got filled up, but we also got destination instructions, so the capacity can never reach, it can never get filled out then, right? Because we keep adding destination instructions as well, so it would basically always be 0 as a running sum. So we'll always be able to take requests, it'll just get added to the queue, I guess. So here get candidate elevator list, it'll check the current capacity, because every time we come here, these destination and source requests, 3 source requests can come in. It's possible that no destination request has come in yet. That's possible. Okay, no, that's fine. It's fine. I think execute instruction is okay. So suppose we are on the capacity, it should ideally just execute the instruction, right? Because if the destination will only come in after the source gets executed. It won't be at the same time. You got a source request, and then for floor 5, suppose someone reached floor 5, at that point we got a destination request, so it has to reach floor 5 at least. So execute instruction does make sense, I guess. We would get potential elevator indices from here, and then once we have those indices, we'll have to sort of decide which elevator will service this request, right? And the parameters we were using is we have to kind of look at the current floor it's on and the current direction. Right, if the current floor and direction, it's possible both are in the incorrect directions. One second. So over here, when we are thinking about direction, if the next request floor, so it's possible that the queue is empty over here, right? So this is only if the length of the instruction queue is greater than 0. Like that's only when we can actually do this, right? There's a case where there are no other instructions even left, in which case the direction would become unknown effectively. We won't know the direction if it's, so we have no other instructions at this point. I think we can add another direction over here. Kind of makes sense to add up, down and neutral, I guess. Right, because in this particular scenario the lift is actually not going in any direction. The self dot current capacity, not current capacity but rather current direction, will become direction dot neutral. And over here, when we are trying to decide which elevator will service this request, for each we get candidate elevator. So in the candidate we also only should take up it's possible to take a request. We are checking for the current capacity and max capacity, and these are basically the potential candidates. So over here maybe we should also check the if the direction is fine, I guess. So we do if the maybe pass in the floor here, right? Maybe get the floor value over here as well, which is of type int, and we can check over here, right, if the elevator dot actually let's keep this function simple enough. We'll add it somewhere else. Yeah, we'll just add it over here. So okay, for each elevator, no, so these are indices, right? For each index in potential elevator indices, index probably, the elevator in question is self dot elevator lists at that index, right? And the direction is equal to elevator dot current direction, and the floor, or maybe the current floor, the floor is already there, and let's say the current direction elevator dot current floor, right? So here so we know which floor we want to go to. So if suppose the current direction is equal to direction dot up, and the floor is strictly greater than the current floor. I mean, this is a condition where it's okay, right? This can be considered, I guess. Like, this is, you know, one of the indices which should be considered. So we need to take into account the direction. So okay, this takes into account the direction, and the other thing we need to take account is the, you know, the diff, right? And the diff would basically be floor minus current floor. So let's keep a min diff, which is some really large number, and the selected index, which is -1 to begin with, right? We get the diff and we say that, you know, if our diff is smaller than our min diff, which, one second, min diff, in that case our diff now our min diff would probably become our diff, and the selected index would probably also become our index in question. So if the direction is up and the floor is, so there are two conditions over here, right? The direction is up, or yeah, basically there can be two ideas over here. If the direction is up, or the current direction is actually equal to direction dot neutral, and the floor is above this, then you do this, right? And you have an LF where the direction is down. Now the direction is down, current direction is neutral, and floor is actually smaller than current floor, which means the same direction. We get this minus floor, and then we do the same thing, I guess. We check if the selected index is equal to that. Why is this? The selected index is not used, but whatever. So we get the selected index. There is another condition, I guess, where the lift is already at that floor, in which case we can just say that, you know, the min diff is probably 0 and the selected index is equal to the index, right? Because this kind of took into account if the floor is greater than the current floor and floor is smaller than the current floor, there is a possibility that it is at that floor, in which case the min diff becomes 0 and the selected index is index. And we've actually found the elevator in this case, so we can actually just break out of this loop. We kind of know. And now we get self dot elevator lists. We add the selected index, so this is the actual selected elevator, and then we call add instruction onto it, and then we pass in the actual instruction now, right? And our instruction used to look like, add instruction takes a floor and a type, and whether we want to add to end or not. We take a floor, we take the type. So why did we add this add to end? Like, depending on if the direction was it was the wrong direction, right? So for example, if we got 3 requests on 2, 3, 4 to go up, we are at 5 currently, and yeah, and 2, 3, 4, and all 3 are going to, we have requests on 6. It's just that the direction is up, but I mean the direction will need to change at some point, to be honest. So maybe we can just simulate it up to that point, and when it becomes neutral, at that point we do it. Yeah, we can even remove this add to end, to be honest, and we can, yeah, and pretty much when a request comes in, it's, no, 1 second, we add instruction. At this point we are checking if it's in the same direction. Okay, so from the point of view of the elevator, we have a we had decided to keep an add to end function which just specifies whether, you know, if it's in the opposite direction we're gonna add to the beginning. But when we did the take request, we checked for the potential elevators, and while checking for them, we checked this. The first thing we checked was whether, you know, these elevators have capacity. Post that, you know, if they have a capacity, we kind of went through each to see, you know, if there's a way in which we can get in the same direction, I guess, same direction or neutral. And, you know, if it's the same direction or neutral, so yeah, this is for the same direction, right? If it's the same direction, this would be false. No, but it would also kind of needed to take into account whether or maybe just take it as a next instruction. The problem with that is if we have, like, we took a request at 0 for 3 and 4 and a request for 2 comes up, what are we going to do? We have to prepend it in that particular case. So I think this made sense, just the logic over here is a bit skewed, right? Because potential elevator indices are the ones which have capacity to take. Actually, it depends, right? It depends. They might not have capacity to take. I think I messed up the messed it up a little. Let's see what can we do to fix this. Our elevators was just taking the next instruction, right? Actually, let's just go online and check what people have done. Low level design elevator system. And instead of wasting time trying to fix that, let's just do one thing and let's check probable solutions for it, and we can just go with, you know, we can just say that okay, this is a mistake we made, and okay, system shall include 3 elevators. So let's check on Geeks for Geeks and let's see what they have done. And yeah, I think we'll just learn from our mistake and we'll understand that, you know, what we were supposed to do, and then we'll just call it a day. So elevators and floors. The system shall include 3 elevator cars. The elevator will service a building that has up to 15 floors, movement capable. So it's pretty much the same. What do you say? The requirements and the scope seems a little similar. So stopping at every floor, outside control panel, inside control panel. So this outside control panel was for like our source request, and this inside control panel was for our destination request. Displays for use case diagram for elevator system. So yeah, they used enums as the floors, which okay, we used integer, could have used enum for the elevator number. For the door action of close or open, which door action to do, there's a direction which is up, down and idle, which, you know, we had the same direction. Button interfaces and in so okay, this is E. use case diagram for elevator. Let's see. So if person press inside button panel, floor selection, allocates request. Let's look at the class diagram once, if they have a class diagram. Button interface, implementation classes, elevator button, door button, hail button, hall button. Okay. Oh, they added a direction in the outside button, so the user kind of presses a direct. Oh yeah, we can take a direction initially, right? What did we not do that in our source request? Our source request add instruction type floor source. Yeah, I just took a floor, right? This should ideally should have had a direction itself. Yeah, when the user is opting for a lift, they should give a direction. Did we not take that? Take request takes a floor and a type. So we got a floor. Suppose floor is 4 and the type is source. We still don't know which. I think that's one major mistake we made. That our design for the source request is incorrect, right? Because in the source request what we ended up doing is when we are taking the request, we did not take into account the direction. Did we miss that? Oh, while writing our classes we did consider that, but I guess we missed it later when we were implementing it. Okay, then we have our display, door and floor classes. Okay, we have display. Okay, panel and elevator and okay, let's look at the elevator and elevator system class. So we had a similar thing, right? Elevator number is fine. We were maintaining that in the elevator system. We have a door panel, display, current floor and direction. They've kept current floor and direction. We had kept in our elevator class, we had kept current floor, direction, capacity. They have not kept. Maybe over here. No. Okay, they haven't kept capacity. So they have a list of floors over here, list of elevators, and the elevator system has a request elevator button, open door, close door, floor request. Floor request. Okay, relationship between classes, door, display, inside panel, outside panel. We have a floor over here. Let's look at the floor request. Floor request. Request elevator, select floor. Interesting. I just wanted to see how they decided which elevator should which elevator should come up. So for example, the press button direction is none, display, elevator car, start ID, moving in direction, stops at fourth floor. So the move function is called as a way to simulate the elevator, I guess. You have a press button which if the floor is greater than the current floor, the direction is up. So the direction gets set over here. Button to press button, set display elevator controller. Okay. And remove elevator. Oh, so okay, so this here there are multiple strategies for the elevator itself. We have a elevator control strategy, first come first serve strategy, in which it's optimized for the person taking it. Poll each request out of the queue one by one. Move elevator. Okay, poll each request out of the queue one by one. Move elevator to the each request. Disadvantage frequent change of direction. Elevators. Uh, Shortest seek time implemented using min heap. So this is the one we wanted to do, right? So this was done using implementing min heap, which is sorted according to minimum distance of requested floor from the current floor of the elevator. It's updated every time a new request is added to the queue. Interesting. So basically what we could have done in this particular scenario is that we needed a way to kind of order those requests, and basically in our situation we could have used min heap, which is ordered on the how far the elevator is, right? We've sorted according to min distance requested from current floor. So this, the one problem I have with this is that I like when we are if we want to sort it based on the diff between the current floor and requested floor, that's not really taking into account the direction, right? If we have a lift system which is kind of going up, and suppose this is the current floor, and we want to calculate the diff to this and to this is 1 and this is 2, but like depending on the direction this is on, this could be different, right? So for example, if the direction of this is up and the lift is currently going down, suppose there's a couple of more floors over here, it actually needs to account for where it will go and stop and change direction. And that's why I don't think it's as simple as just doing this, because we'll need to understand which direction it's going in. The other, I think, option is that we say that if there is a lift which is going in the opposite direction, we just don't take requests, right? No requests are considered if the lift is going in the opposite direction. So only if it's going in the same direction plus or it's neutral, in those two scenarios we can take requests, and we can say that okay, if it's going in the opposite direction, we just say that we're not going to take a request and we're just going to keep ticking. So I think that is what we were doing here when we had said that we'll check for the direction, and if it's in the right direction, we're going to take the request. Otherwise we are just probably not going to take the request and we're going to wait. But yeah, I think add to end wasn't as simple as I had thought, that maybe we add it to the beginning or the end. It's possible that the request comes in the middle. That's the problem. Like for example, if we have this and we have like 1 2 3 4 5 6 and our request is coming in, suppose we got a request for 3 5 and 6. Suppose we have 7 floors and the request came on 3 5 and 6 to get people, and all of them want to go to the 7th floor. Currently we are at floor 2 and we get a request on floor 4 to go to 7. In our lift's instruction queue, it won't be in the instruction to stop at 4 won't actually be in the beginning or the end. It would be in the middle somewhere, right? Yeah, I think we didn't take this into account. If we had taken this into account, we probably would have done something in a different manner, right? So if we don't think about the code right now and we just think about what kind of an algorithm we would have wanted to use to solve this, what would that look like? I guess if we get a request, which is, either we'll need to know these two, the current destination, if it's hmm. 3, 5 and 6 are the, we'll get a 4, and effectively our current changing. I think this is what it was saying, right? So I think, yeah, so I think this is what this is saying, the min heap approach. It's saying that, yeah, I think I understood the min heap approach at least. What it's saying is that if the lift is going in the opposite direction, we are not going to take a request, right? So for example, if the lift is going in this direction and we get a request to go in this direction, we're not going to take it. We only take requests on a lift which is either idle or it's going in the opposite direction, right? And then you basically, your requests would all be in the same direction, and then you can actually use a min heap based on the diff, right? If we eliminate requests which are in the opposite direction and only consider requests in the same direction, then we can probably use this min heap and diff, in which case what will happen is, in this particular scenario we'll have 3, 5 and 6, right? So our min heap will have 3, 5, 6, something like that, and suppose we get a 4, right? And that 4 will basically get organized over here. It will be now 3, 4, 5, 6, right? And when we reach 3, this 3 will get removed, and then we'll have 4, 5 and 6. Yeah, that makes sense. So basically what we wanted to do, or what we had to do in our code, is we needed to not take in requests that are coming in the opposite direction and wait for an elevator to be in a neutral state or to reach one end, right? And the other thing that we needed to do is we needed to use a min heap to manage the requests. I think if we would have done those two things, it would have worked out. But okay, it's an interesting question. I don't think I'll ever forget this. It says that the disadvantage starvation of distant floor when maximum request keeps coming from nearby floors. Why would a starvation take place? Like suppose this is our floors, and suppose there's a request over here and it's saying that a lot of requests are coming from nearby floors, it won't reach this floor. But those requests would be to, like, suppose, but like we won't take if there's a change in direction, right? If there's a change in direction, then we won't take those requests. So I don't think it'll get starved. Worst case scenario, I think it'll just stop at each floor before reaching this, because before the direction gets changed, we'll probably service this. So I don't think this is completely, I'm not sure exactly what this starvation, why this starvation would happen. Anyways, I think that's it for today, and that's it for low level design. I would have loved to completed this question, to be honest, but I think it's okay. I'm kind of tired, so let's call it a day.